Okay, what we did yesterday is kind of leading up to this. We started looking at the concept of integrals. And I noticed today we're talking about definite integrals. What does that mean? That means we know the interval that we're talking about. So look at this definition. These are called Riemann sums. We're just talking about a series of x values here. And so these x values divide an interval up into little subintervals. And it's reminding us that delta x sub I is just the width of those little subintervals. That's all that's saying. You can study this. This doesn't make that much sense. I mean, yeah. It's a definition, and we need to pay attention to definitions. But just realize that's called a Riemann sum. Very much like we did yesterday. So next page of the notes, they're saying the norm is the width of the largest subinterval. Well, I wouldn't worry about that a whole lot because we're going to be using subintervals that are all the same width for the most part. And in all the calculus books I've seen, I've never seen the term norm until we get to this calculus book. And it's going to translate pretty quick into something we do realize in approaching infinity. Now, this is talking about the norm we're going to see approaching zero. Well, that's just another way of saying in approaching infinity. And then we get to this concept of definite integral. Okay. Here's that delta epsilon concept. You give me how close you want to be, and I'll tell you how close the x value has to be. Very formal. Notice one thing, though. We get down to the bottom of this definition of definite integral. It's telling us right here that as the norm goes to zero, well, this stuff inside the summation looks exactly like it did yesterday. And then we change it to this, equaling this thing over here on the right, f of x dx. And look at the notation. See the little a and the little b? That's saying the interval is from a to b. That's why it's called a definite integral. We're not just talking about this thing in general. We're talking about on this specific interval of the x-axis from a to b. Okay, you can read over that. Let me give you a different view of it, maybe. So I'm going to change that as the norm goes to zero to n is going toward infinity. And I just sketched a little graph over here. And here's what I'm going to do. I'm going to take the interval by subtracting a from b and dividing by the number of rectangles we want. Well, I'm just putting n. This is a general kind of thing because I want to find the area here. And we're going to use a definite integral to do that. So I find that first. And then here's the part I really want you to get a handle on. This page is not in your notes. If we're starting at a, I'm just drawing this really big. Let's assume this is our first little subinterval. The width of it is what? Delta x, which means this x value with the red arrow pointing to it, wouldn't that be a plus delta x times 1, if that's my first one? This is the point that is going to lose you. Thank you. This is the point that's going to lose you if you don't get it. Where the red arrow is pointing, the x value is a plus 1 times delta x. I'm just adding delta x to a. Okay, and then I go up here to where it intersects our function, the blue line. And if I go across to the y-axis, isn't that just f of a plus delta x 1? So I'll do another one. I'll come over here. This x value, where the purple arrow is pointing, is just a, where we started on the interval, plus 2 times delta x. I'm just adding delta x's as we go. Now remember, delta x could be any width, but we're gonna want to see what it does when it shrinks to 0, and that's what that norm definition is talking about. Okay, and if I go across up here, isn't my y value just f of a plus 2 delta x? Yeah. Okay, keep that thought in mind. So I'm going to say, I'm taking this first idea of a limit up here, and I'm just plugging in what in my generic x values are. I'm saying x inside these parentheses is just a plus some number of times delta x. Because I is going to go from what? 1 to 2 to 3 to 4 to 5, 6, all the way up to as close to infinity as we can get. And that's where this summation idea really comes in handy. If you didn't understand the summation stuff before now, this won't make any sense. Now then, I'm going to say, if we figure out that limit, that's the same as this definite integral, f of x dx, from a to b. In other words, going from a to b here, the area under the definite integral, we'll give an area out for a second, the definite integral in here is what that represents. Okay, let's really do one. So I've got a is 2, b is 5, and my f of x is 4x plus 3. So the first thing I do, I find out what's my delta x. And so what do? I take b minus a divided by n. And again, I'm just saying generic n because that's what's going to be going toward infinity. So I get 3 divided by n. That's our delta x. Stop me if something doesn't make sense. I'm just fleshing out what we just said in a generic form on the previous page.
Okay, so the change of x is b minus a over n.
And in this particular case, it's 3 divided by n. Because we're going from, let me do this, we're going from 2 to 5. Okay. So I start writing out limit stuff. You might want to jot this down. Nope. Nope. I want you to see it from this perspective because it'll make the homework easier. They were not in the printed notes I got. So just turn over the back page. I think it's blank. Okay, so I'm going from 2 to 5. That's my interval of this function. And we know the function. And notice the notation. The integral notation here says I'm going from 2 to 5. And I'm putting my f of x in there. And I don't want to leave out delta x because I'm getting rectangles again, right? That's that rectangle concept. All right? We're going to be writing limit a lot here. So first of all, I've got 4 times what? That 4 right there is the 4 for the x up here. So inside the blue parentheses, I've got to put what my x is in terms of I. So isn't it that? If 3 over n is delta x, then that is the same as delta xi up there. But that's not the end of my f of x. I've got more to f of x, so I add 3 to it because our function is 4x plus 3. You're exactly right. So inside the red brackets is my f of x in terms of delta x and I. And then the 3n on the outside in black is our delta x. Because I'm on an area. What next? I can do this. I just foiled it. Not FOIL exactly, I just distributed the 4. So I'm saying 4 times 2 gives me 8. 4 times 3 over n gives me 12 over n, I. And then I add my 3. So inside the parentheses there is just that thing with the 4 distributed. Now I'm seeing some constants in there. And out the end is my width still, my delta x. Okay? Equals the limit as n goes to infinity. I added the 3 and 8 together. We're taking this step at a time. And I put in a bunch of steps so that you can see what's going on. Have I made a mistake yet? Always double check me. That was my thought, but that doesn't always pan out. Okay, so now then, I'm looking at that. The 3n out here on the right, I'm not seeing an I involved with that. That's not going to change. So I can pull that out, put it in front. Things are getting simpler. That equals this limit. And notice now I'm splitting these apart. I've got a constant 11. I know there's just going to be n times 11 for that, based on yesterday's notes. So I've got 11n. I'm seeing 12 over n times I out here on the right. So I just pull the 12 over n, which is constant, out. And that leaves me a summation of I from 1 is I is going from 1 to n. And we've got a shortcut for that. Putting a lot of pieces together here.
So you got 11n, or is that one of the...
If I'm summing a constant, I'm adding 11 n times. So that's just 11n. Whatever n is, I'm doing 11 added up that many times. So that's where the 11n came from. I pull the 12 over n out because it's a constant. So I'm getting this. The 3 over n times 11n is for that constant. I'm now distributing the 3 over n. So it appears by the 11n and then by this thing. And the n times n plus 1 over 2, that's my shortcut for summing I from 1 to n. Well, before that, I can do this. I can start canceling stuff. So over here on the left, I'm seeing 3 times 11 over 1. So that's going to be 33. Over here on the right, I'm seeing 3 times 6 times n plus 1. And on the bottom on the right is 2n. So let me clean things up a little bit. All that, don't forget, is a limit. So 33, like we said, and then plus this. I distribute the 18. I'm getting that. Let me stop a minute, and if you want to jot that down, you can.
So now we take the limit of it?
Well, I can put one more step in. You could probably look at that and tell me what the limit is. But I'm going to go ahead and divide. I'm going to split my numerator, 18n over n, and then just 18 over n. And now it gets pretty easy to tell what's happening. The 18 over n out here on the right is going to go to 0. 18n over n, the n's will cancel, and that's just going to be 18. Right? So I add those together, and the limit is going to be 51. What does that mean? That means the area of that little bounded figure is 51 square whatevers. Could we have done that another way without all the calculus? Yeah, how?
You do 3 times 2 and then you do the triangle.
What's f of 2?
8 plus 3 is 11.
Okay, so where that coming up from 2, f of 2 is 11. So that'd be right there. So that means it's going to be 11 over here. So I could say, what, 3 times 11 is what?
33.
And bingo. So that's the area of the rectangle on the bottom. So we can figure out the area of the triangle on top of that is going to be 18. So we could have done it geometrically. But I want it to make sense with this idea of Riemann sums.
You can't do that with exponential ones.
No, or with curves.
Yeah.
But it works out really sweet with this. Okay, let's keep going. A little bit of reading to do. This, in a nutshell, is saying if a function's continuous, we can integrate it. That's a general rule. If a function's continuous on a closed interval, we can integrate it. And it's giving us a little warning down here. With this section of homework, we're almost always going to be doing things the long way, meaning like that. Think of all the character you're going to build. Okay, we good so far?
Yes.
It might take some soak-in time because this is just weird enough. All right, I'm looking at this function. F of x is 2x. So y equals 2x. And they want us to integrate that from negative 2 to 1. So that's what that drawing is representing. Using the limit definition. Now when we get to section 4.4, next week, it'll be really fast. Really fast. But we're having to use the definition here. So first thing I do, I'm saying I'm going from negative 2 to 1, so I subtract 1, take away negative 2, and our delta x is 3 over n again. Nothing special about that, it just worked out that way. Next step. Kind of plug it into this general idea. So in blue, what do I have? Every place I see an x up here in my f of x, I'm replacing it with negative 2 plus delta x times I. Why? Yeah, where did we start in this one?
-2.
Minus 2. You're right. So I've got to say minus 2 plus all these little delta x's. Minus 2 is our left endpoint, in other words.
So we replaced x with negative?
No, sir. We replaced x with negative 2 plus however many delta x's we're adding to that. We're working our way from that left-hand endpoint to the right. So we're starting out here at negative 2 and coming over to 1.
So why would it place an I by the change of x?
Because I'm going to keep adding I'm going to keep adding delta x's to this for each little rectangle. Okay. And then my delta x in black is the width again of each rectangle. So then we make it a little more in the problem, as it were. And so on the inside, notice delta x is being replaced by 3 over n, which is what delta x is for this problem. And on the outside, I've got 3 over n, which is delta x, which is the width of the rectangles. Don't get confused about, both of these 3 over n's represent delta x. One of them is being multiplied by I, as I changes from 1 to 2 to 3 to 4 and so on. The other is just a constant 3 over n. All right? I just distribute the 2, I'm getting this.
Can we write the whole sum thing?
You know, while you're taking notes, I would just abbreviate it. Just put limit if you want to. I wrote it all out.
So why would you not take out the 2 into account since it's a constant?
Could. I'm not saying this is the only way to do it. It's going to end up out there anyway.
Okay.
Right. Yeah, good point. So really, I could have taken out 6 over n, right?
Yeah.
On this one. That would work. Yeah. Okay, so now then I've got a constant -4 and a constant 3 over n and a constant 6 over n. I'm pulling the 3 over n out. If I said n was 1,000, that's a constant. I can pull it out. N in effect is a constant because it's going to approach infinity. Every step along the way is still going to be a constant. All right. Yeah, I am showing too many steps. So I'm splitting the summation into summing -4 n times and summing summing 6 over n I times. So I could have shortened this. But I really am trying to drive home the point that we can split these things apart and use our shortcuts on each of them. So if you don't want to write that one down, you don't have to. You don't have to anyway. So over here, summing -4 n times gives me this -4n. I just put it over 1. And then I'm pulling on the right-hand side, I'm pulling the 6 over n out. But I can't forget that that's being multiplied by 3 over n. So I'm distributing the 3 over n to each one of these pieces. It looks like I left a bracket off out here. Yeah, I did. On the right-hand end. Imagine there's a bracket there. I start canceling stuff. And so I'm seeing on the left-hand term, -12, and on the right-hand term, 9 times n plus 1 over n. So I'll write that down. And this is starting to look like the last problem here. You could stop right there and say, I know what that limit's going to be. But did I do that? No, because I want to show all my steps just in case somebody's having trouble with this. So there we go. So the 9 over n out here on the right-hand end is going to go to 0. The n's are going to cancel on this one. So I've got -12 plus 9 gives me -3. Anybody have a problem with that? You sure? When's the last time you saw an area that was negative?
Nothing surprises me anymore.
Oh no, I know the feeling.
Is it just the absolute value?
Wait,
no, it's because part of it's positive and part of it's negative.
Part of it's positive and a bigger part's negative. There's a moral to that story. You got to watch out. What kind of thing am I finding the area of here? This has a large part that's negative below the x-axis. A smaller part that's positive. Now, if I truly wanted to find all of that area, I would have to do a trick that we're going to see at the end of the notes here. But doing it like this, you get into trouble. So it helps to sketch out what you're talking about. If they gave you a drawing like this, the bells ought to be going off. Because you can see part of the area is negative. If those two areas were the same size, you'd get an area of 0 after all that work. Not be good. You wouldn't be very happy about that. Okay, so more reading. And it says, to have a definite integral representing an area, make sure that the area is non-negative. And then this is pointing out a fact that I've been alluding to. If we have a definite integral from a to b, that represents an area. We're going to be writing it like this most of the time, like in Theorem 4.5. So in this pink drawing out here, first one, from a to b, this pink shaded area would represent the definite integral from that. So here's a graph of the function down here at the bottom, 4x minus x squared. Well, we know it's a parabola. We're going from 0 to 4. So this is all positive here. So this would be a great candidate to find the area of, using the techniques we just talked about. We're not going to find that one, but I just want you to see, before you jump into something and start wasting a lot of time, make sure you're talking about a positive area. Okay, this page is saying something we already figured out a minute ago. You don't always have to use calculus unless it tells you to. Some of these you can solve geometrically. Look at A. Look at A. If I sketch that drawing, I'm going from 1 to 3. There's my base. What's f of x? 4. So I can do that slightly faster than doing that long calculus way. What's my area?
2 times 4.
Yeah. 2 times 4. Always helps to sketch something out. I'm not talking about an elaborate drawing like we had to do with all the concavity and stuff. Okay, look at this next one. I make my little sketch. We're going from 0 to 3, and that's just a straight line. And I could solve that like we did the first problem back there. I could say, I'm just going to divide that and put a triangle on top and a rectangle on the bottom. For the triangle, I know it's 1/2 base times height. So I've got 9 over 2 plus 6. So the area of that thing is 10.5. Could we solve it with calculus? Yeah. We already did one almost exactly like that. Look at this next one. What kind of graph is that going to be?
Curve.
It is, but a special kind. Semicircle. Glory be. All right, so it's going from -2. The interval is -2 to 2. But that's a semicircle. What's the radius?
2.
And I'm only taking half that circle's area, so it just comes out to be 2 pi. Would pi be involved if we did this with calculus? Yeah, it'd be a constant that got pulled out, right? Now notice that can't be a full circle because then it would be a function anymore. If I wanted a full circle, I could split it into 2 different functions. But no need. I just double one of them. We're almost there. 2 special definite integrals. Look at number 1. What's special about that? What's my interval? A to A. How wide is that? It's not. So the area is 0. Surprise, surprise. Look at the second one. What did they do there? Going from B to A. Notice what happens. It flips the sign of the area. Work one out, you'll see. It flips the sign.
But isn't B to A just your starting point?
A to B. A is the leftmost point. B is the rightmost point.
Oh.
So I'm going from the rightmost to the leftmost.
Yes, sure.
Well, think about it like this. If I'm starting at the right-hand end, that would be B. Then what am I going to do to get to the next rectangle to the left? You're going to be subtracting values. Okay, so look at A. Going from pi to pi for sine. 0.
Easiest trade there.
Mm-hmm. Were they all like that? That would be so nice. Okay, look at the next one. This is going from 3 to 0. Now, we already figured that problem out. It was 10.5.
But it'd be minus this time.
Yeah. So always watch out. What are your
So when
endpoints of your interval? Sorry.
so when the
Well, just picture your interval in your head. It's going from A to B. A is smaller than B on the x-axis. What if you started out there at the B end and worked your way back? It's going to be a negative area because you're subtracting delta x's as you go. Okay, one last little thing here, I believe. Well, nearly. This is saying we can split these definite integrals into parts. Now then, they're making an assumption here that they didn't say. I've got 3 closed intervals determined by these points A, B, and C. Look at what they're saying. I can split that into the integral from A to C and add that to the integral from C to B. What are they assuming? C's in between A and B. They're just saying, go from the left end point to some point in between on the interval, and then go from that in between point to the right end of the interval.
that makes a good amount of sense.
It does. It really does. Now then, going back to this one. If I really wanted that area, I could divide my integral up from -2 to 0, take the absolute value of it, and then add that from 0 to 1. I could do that if I really wanted the area. I can split them. I don't have to go from one endpoint to the other. And then down at the bottom it says, well, you could do that with absolute value, because absolute value would be one area coming from the left and a different one coming from the right, because the definition of absolute value is different. But wait, there's more. Sounds like a late night commercial. Something we might have suspected if we'd stopped to think about it. If k is a constant inside the integral, I can just pull it out. Well, that's what we've been doing on the limit versions. That comes in handy sometimes. And the second one is, if you've got 2 functions added together inside an integral, you can split them, treat them separately. And it reminds us, areas are all greater than 0, and bigger areas are larger than smaller ones. Okay, all right, let's see what they're talking about there. They're telling us that definite integral is no smaller than 0. You're not going to have a negative there from A to B. Again, look at the interval. It starts at A and goes to B. And at the bottom, it's reminding us that given the same interval, if f of x, if the integral of f of x is less than or equal to the integral of g of x, then unless they are equal, the area under the f curve is going to be less than the area under the g curve. That's all it's saying.
Yeah,
That makes sense. Okay. Questions, y'all?
I think I'm about exhausted.
I know. I know.
Thinking, so.
This stuff is like somebody beating you with a stick sometimes, especially